project, so nozzle, the last component from my engine. We just went through diffuser, sort of said 2 and 3 are equal, 2 to 4, 3 to 4, and now we're going 4, 5, 6. Okay, so we're going to assume isentropic. For ideal ramjet, no losses, which is the same thing that you're doing with the experiment project. So that means my P stagnation 6 is equal to my P stagnation 4. So if I know my stagnation pressure coming out of the cluster, I can figure out my stagnation pressure in station 6. I'm going to assume, well, it's a CD nozzle. I don't have any heat addition. I don't have any heat or friction that is being done here, so Q equals to work equals to 0. So from that, my stagnation, since it's isentropic, stagnation temperature is equal to the same T max that I'm going to get throughout. That's important because with 1 T max, you're generating through the combustor. Now you're expanding it and accelerating that gas. You want to bring that gas all the way to lower temperature as possible. Any of you compute the temperature for the project? Did I ask you for the project? No? Try to compute the temperature you just said. See what it's like. You'll be surprised. You should get almost 150 Kelvin. So
in the channel?
it's pretty freezing in there. 150 Kelvin, that's minus. In the minus degree. So that'll be your static temperature. The gas is going to be so full. We're actually having, well, somewhere we go. The temperature in the tank. Well, because that's based on the question that was brought up a couple of days ago that said, what is the temperature that we need in the gas? Well, the tanks are stored externally. So they're seeing the external temperature. So I told you, take it as 300 Kelvin. So if you take it as 300 Kelvin, you're going to realize it's actually significantly low. But yeah, try it out, see what that's like. It's fun. How can you try that? If ideally expanded, obviously P6 is equal to P ambient is equal to my exit pressure. So that's equal, so I use my stagnation properties to figure out my pressures equals to 1 plus gamma minus 1 over 2 m6 squared gamma over gamma minus 1. Keeps repeating. And then we already said this is P's. So based on that, I could say, well, P stagnation 4 is equal to P4 is equal to 1 plus gamma minus 1. 4 squared gamma over gamma minus 1. Now we're assuming if gamma is constant, the Mach number at the exit is going to equal to, so it depends on scenarios, but if you're trying to accelerate the vehicle or the aircraft, you might choose that the exit Mach number be different than the free stream, or you can choose conditions where it's equal to the free stream. So certain scenarios where I just want to cruise, therefore my exit Mach number is equal to my flight Mach number speed. So that's one condition that you want to keep because it depends on how you're running your engine. You could run the engine as an accelerating thrust propulsion system, meaning that I need to go from Mach 1 to Mach 1.2 in terms of the flight condition. I'm at Mach 1 and I need to go to that condition, or Mach 2. So I need to accelerate the engine, so I need to expand my gas faster. But then if I'm cruising, my exit Mach number is going to be equivalent to my flight Mach number, because I'm generating just enough thrust to equal my drag. Okay, so if
if gamma actually is not equal to gamma ambient, Mach number exit is not getting equal to, that's not okay. And now, based on this, I have U exit is equal to M exit square root of R T exit, which you already know. And I can take all that information and substitute it into my specific thrust, which that's what we're after for all this propulsion stuff. Gamma TA multiplied by 1 plus F. All I did is multiply, they put the velocities in there, so you have an equation for it. TO4 over TA multiplied by 1 plus gamma minus 1 over 2 m squared power minus 2 minus 1. And this is equation 5.27 in total. Ideally, you don't want to use this directly because it has all the components. What you want to do is compute your different properties and go back to what we drove as our equation for it, which is this. And most likely, you're going to end up not using this much. You're going to be using this. All this is this just has all the terms in it. Okay? All right, so I think we're ready for an example problem. So let's do an example problem. All we're doing is going to take all these equations and start putting them into numbers. All right, so sample problem. Ideal ramjet, and actually the real ramjet is straightforward after we do the ideal ramjet. I've got a ramjet at Mach equals 3 at 10,000 meters in altitude, which that translates into my ambient condition of 223 Kelvin, and my pressure is equal to 26,500 pascals. Determine thrust, super thrust, PSFC for the following. I'm giving you T stagnation temperature is 2,500 Kelvin. Heat of combustion is 40,000 kilojoules per kilogram, and my area exit is 1 meter squared. All right, so list my assumptions. I'm assuming an ideal ramjet, so isentropic. P stagnation is constant for my free stream. Ideally expanded. That's a critical one because P6 is equal to P ambient is equal to P exit. You can't assume this for the project that you're doing and certain scenarios, but just for simplicity's sake, we'll do this. But we already know how shocks behave. And constant gamma equals 1.4. We're going to take gamma 1.4 for now, but eventually we will expand to a variable gamma, and I'll have you do this in part of the homeworks. We'll ask you to vary the gamma inside the engine at certain stations, and you will see the effect of gamma on this process. And it's driven by combustion. The fact that you're heating it. It's not just air. Kilograms per Kelvin, and I'm gonna make assumption that, for now, that my fuel to air ratio is less than F stoic. Bless you.
God bless you.
All right, so based on this, let's solve the problem. So, what do I need? I need thrust. So, thrust is equal to MA multiplied by 1 plus the fuel to air ratio, U6 minus U, plus my pressure ratio, multiplied by A6. Now, one thing I already know is my exit pressure and ambient pressure are equal. So what does that mean about that term? 0. Ideally expanded. Alright. So now that I got that term, what do I need? Or what do I have? I have the Mach number at the inlet. I have the static temperature. I can compute this velocity. I already know my fuel to air ratio. Do I have my fuel to air ratio? No, I don't. How do I get my fuel to air ratio? Yes, exactly. Beautiful equation that we have right here. You just plug in these values and then you get fuel to air ratio. But I need primarily my exit velocity as well, U6. So based on this, well, U is equal to, so finding U is equal to Mach number multiplied by gamma RTA, well, that's equal to 3 multiplied by 1.4 multiplied by 287 multiplied by 223 Kelvin. Okay, and that gives you 898 degrees seconds. And the exit is equal to the same, and the inlet is equal to P6 U6 multiplied by area 6. Okay, so P stagnation at the inlet is equal to P stagnation at the exit. And according to this, P6 is equal to P ambient of the rate of thrust. So what that means is my exit Mach number is going to equal to M, which I have it as M, equals to my plot Mach number, which is 3. So that means I'm at cruise conditions. My exit Mach number for the engine is almost exactly the same as my free stream velocity, which is my aircraft velocity. So I'm not accelerating or decelerating. I'm just cruising. Therefore, T stagnation 6 over T6 is equal to 1 plus gamma minus 1 over 2, M6 squared. And I already know my T stagnation 6 is equal to my T stagnation 4. So based on this, it's equal to 2,100 Kelvin because it's Tmax and it's isotropic. So from this, I get my static temperature, T6, is equal to 2,500 Kelvin divided by 1 plus 1.4 minus 1 over 2. The Mach number squared is 6, so 3 squared is equal to 892.9 Kelvin. Does that make sense? If the ambient temperature is 223 and I'm at a much higher temperature in terms of my static temperature, yes, I'm burning, so therefore it's going to be high. I could use this temperature to find out my density if I'm trying to find the mass. Well, density 6 is equal to P6 divided by the real mass constant multiplied by T6. Well, P6 is equal to P ambient, so I already know that one is 500, pascals divided by 287 joules per kilogram multiplied by 892.9 Kelvin. So from that, we get 0.103 kilograms per meter cubed. Now take that and substitute, or actually we have Mach 6. So Mach 6 U6 is equal to Mach 6 multiplied by gamma RT6. Gamma's constant, so I already know my T6. Then that's equal to 3 since I'm cruising. 1.4 multiplied by 287 multiplied by 892.9. And what I get from that is 1,797 meters per second. So now that I know my velocity, I can get my mass through my engine. My mass through the engine is equal to rho 6 multiplied by u6 multiplied by area 6, and that's going to equal to 185.1 kilograms per second. That's a substantial, that's a substantial amount of flow that I'm putting through my engine. Now, I know my M exit. I need to find out my the amount of mass that I'm putting in. Well, the amount of mass I'm putting in, MA, by definition, is going to equal to M exit divided by M plus amount of fuel. So meaning that M dot A plus fuel times M dot A, which gives you M dot fuel, is equal to M dot exit. So all I'm accounting for is the amount of fuel. So if I know my fuel to air ratio is based on stagnation temperature over stagnation ambient minus 1 divided by heat of combustion divided by CP TOA minus TOA4 divided by TOA. That's the same equation we already wrote. So I need to know my stagnation temperature. Stagnation temperature is already based on my population 1